The votes are in, and it has been decided that the first question from Dr. Laude's acid-base worksheet that you want me to answer is question number 15. What is the pH when no lithium hydroxide is added to 200 milliliters of 0.5 molar CH3NH3Br, or methylamine bromide? We were given earlier in the worksheet that the Kb of methylamine is 10 to the negative 6th. Okay. The first thing we have to figure out is what exactly is this species right here. What do we have? Okay, CH3 and H3Br is a salt. Okay, we know that it's going to dissolve completely in water, which means it's going to leave us with CH3 NH3 plus. And if you have a cation in solution, and you know that the cation is going to act as either an acid or a base, you have to recognize that if it's a cation, that means what it really is BH plus. Right? BH plus. This is a plus sign. Okay. This is BH plus. BH plus is the conjugate acid of a weak base. So if I have a conjugate acid of a weak base, what I really have here is a acid, HA. Okay, I can call this BH plus, I can call this HA. It doesn't really matter. They mean the same thing. We're going to pick whichever one is going to make our lives easier for this particular problem. And since we are looking for pH, the easiest thing for me to do is to treat this as HA, an acid, because then I can directly solve for a proton concentration. Whereas if I was using BH plus, I would have to recognize that the BH plus would be combining with hydroxide to make water and our base. And in that particular case, I don't have a direct way of solving for protons. I would have to solve for the concentration of OH minus, turn that into POH, and then solve for pH. And that's a little more complicated than I feel like doing, so I'm not going to do it that way. You can, it would totally work, but more work than you want to do, I imagine. So I'm going to start by calling this HA and ignoring all this messy junk. Doesn't really matter. This is just HA. It's my acid with a proton stuck to it. Okay, it's HA. And I know that in water, HA is going to dissociate to some extent, and it's going to form the conjugate base A minus and H3O plus, which is the same idea, same thing as H plus. Same thing, okay? Same thing. For the purposes of our math anyway. All right. I also know that if I'm using an acid dissociation, then I need an acid dissociation constant. Not Kb, what I need is Ka. How do I get Ka when all I have is a Kb? I have to recognize that Kw is equal to Ka times Kb. And if Kw is equal to Ka times Kb, that means that Ka equals Kw over Kb. I know that Kw is always equal to 10 to the negative 14. The Kb that I was given was 10 to the negative 6, which means that my Ka is equal to 10 to the negative, math, 8. Okay. That's worth knowing. Now that we have that under our belts, we can take a second to do a rice table. Okay, this question asks us to think in the case of 200 milliliters of 0.5 molar CH3 and H3Br. Why does it matter how much we have? In this case, it actually doesn't, because we're not doing a neutralization reaction. We're adding no lithium hydroxide. So all we're really doing is dissociating 0.5 molar methylamine, or the acid form of methylamine, I should say. So that means I'm going to start with 0.5 molar HA. Don't care about water, it's a pure liquid. I'm going to start with no conjugate base and no protons. I'm going to lose some amount of HA. I'm going to gain some amount of A minus and gain some amount of protons or hydronium ions. Again, same thing. This is my Rice table, and I know that these are my equilibrium concentrations, which means these are what I can plug into my equilibrium constant expression. That's our AP exam buzzword, the equilibrium constant expression. That thing where I say that my equilibrium constant is equal to my products in their stoichiometric ratios, raised to their stoichiometric coefficients, so 1 and 1 here, divided by my concentration of my reactants. Okay. And I can plug in all the stuff I know, which is that Kb is 10 to the negative 8th, and it's equal to my concentration of protons times my concentration of conjugate base divided by my concentration I started with of HA minus the X that turned into conjugate base and protons. Okay, so this is the same thing as x squared over 0.5 minus x. Now, I have two options here. I can do some really annoying algebra and solve for x, or I can avoid the really annoying algebra by recognizing that this x right here is negligible. Okay, I can zero that out. It is negligible. How do I know it's negligible? I know because my Ka value, 10 to the negative 8th, is much smaller than the concentration I'm talking about, which means that with significant figures, subtracting some amount that is around the same order of magnitude as my Ka value is going to end up being the same thing I started with significant figures. Okay? So, when I recognize that, I say that the x on the bottom is negligible. I'm going to come back over here. 10 to the negative 8th is equal to x squared over 0.5. Okay? Okay. Multiply both sides by 0.5 to get 10 to the negative 8th times 0.5 is equal to x squared. So if I want to get just x, I can take the square root of both sides. And I'm going to find out that x is equal to 7.0711 times 10 to the negative 5th. Okay, what is x? Earlier in my Rice table, I said that x was my equilibrium concentration of my conjugate base and my equilibrium concentration of my protons as well. So x is equal to A minus, and more importantly, H plus. Why is H plus more important? Because I'm looking for pH, which means that I can find the negative log of my H plus concentration, x, 7.0711 times 10 to the negative 5. And if I plug all of this out, I believe you get 4.15. Addendum. So I just looked back and realized that I did this entire problem with it being 0.5 molar, but the original problem said 0.05, so I've gone back in and fixed it in crucial places. So we end up with 10 to the negative 8 equals x squared over 0.05. Put that in the square root, 0.05. We end up with x equals 2.23 times 10 to the negative 5. which is equal to our conjugate base and our proton concentrations. The negative log of 2.23 times 10 to the negative 5 is 4.65. So the key was right. I just need to watch what I'm writing when I copy things down off the internet. Okay, sorry about that. Thanks. Bye.